Okay, in this chapter we're going to be studying the chemistry of enolates and enols. We're going to be able to predict the products of reactions of enolates with alkyl halides, aldehydes, ketones, and esters, draw mechanisms for intermolecular and intramolecular versions of those reactions. So first we're going to discuss the aldol reaction. And it can be catalyzed by acid or by base. First we'll do the base catalyzed mechanism. You can see that what we're going to be doing is making a bond between the carbonyl carbon and an alpha carbon of another molecule of the substrate. So I'll go ahead and map those on. Here we have 3 carbons, and if we use another color for the other molecule, let's say blue, there's those 3. Okay, so this is the bond that we're going to be building, the carbon-carbon bond between this position, between this position and this position. So I've gone ahead and numbered these here, and so what we need to do is build a bond between carbon 2 and 4. We can see carbon 4 is an electrophile, and so what we need to do is convert carbon 2 into a nucleophile. We're going to do that by removing a proton from this position to make an enolate. Now you might have thought you could just deprotonate here and put the negative charge on this carbon, and that's technically correct, but it's not the best way to do it, because if we look at those 2 resonance structures, we can see that actually this is the more stable resonance structure because it has a carbon-carbon double bond, and the negative charge is being carried by oxygen, which is the more electronegative atom. Okay, whereas here we do have a carbon-carbon double bond, a carbon-oxygen double bond, but we have a negative charge here on this carbon. Okay, so in reality, enolates sit primarily in this form, and they have stereochemistry that is relayed to the substrates, as we'll see later on. So you want to always draw it this way, even though our very next step is going to be to push those electrons back down and use this carbon as a nucleophilic position. So we bring our electrons down, and now we're going to use these electrons in the pi bond to attack the carbonyl and give electrons to oxygen. Finally, we're going to protonate our alkoxide here to give the final product. And that also regenerates our catalytic hydroxide. So now we're going to look at the acid catalyzed version of this. So we're going to have aqueous catalytic acid. We can go ahead and draw our water, do this protonation, and make H3O+. And now we'll activate our carbonyl. Water will come in and deprotonate to form the enol. And we'll go ahead and react with a second equivalent of the activated aldehyde. And now we simply need to deprotonate with water to access the final product. Remember, the resonance form of this enol is shown here, and we always can use our minor resonance form to guide the reactivity. So that tells you where you're going to be making your carbon-carbon bond. You're not making it to this carbon here, you're making it to the alpha carbon. Okay, and we see that here. That's the carbon alpha to the carbonyl. These products are called beta hydroxyketones, and they are actually prone to further reaction. They can eliminate in the presence of acid and heat. So the aldol condensation is just a continuation of the aldol reaction. The condensation refers to taking water out of the product and bringing that water into your reaction solution. Kind of like the condensation on the outside of a cup takes it out of the air and puts it on the side of your glass. Again, you're going to have the two pieces of your molecule coming from two of the starting material, and the mechanism for the acid catalyzed aldol condensation is the exact same as for the aldol reaction, except that we're going to go ahead and eliminate water in that last step. So just for practice, we'll go through the whole thing again, and then we'll focus on that elimination step. Okay, so we're going to do the acid mechanism. We're in acid, so we have to protonate our carbonyl before we can add any nucleophiles or do any deprotonating. Next, we can go ahead and deprotonate at the alpha position to form the enol. The enol is going to add to another activated carbonyl. Don't forget to put this proton on here. It's going to be very important to the reaction actually working. Okay, so we're going to reform our carbonyl here. We're going to use the pi electrons as our nucleophile. Okay, so now we have a new activated carbonyl and we have a new alpha hydrogen. And so we actually are going to have a keto-enol tautomerization here as well. When we don't have heat, that just happens until we work up the reaction. But when we do have heat, we get something else going on. So let's look at that. So sometimes we're going to just go back in this direction, but sometimes this this alcohol is going to get protonated by H3O plus to give an activated leaving group. And when that does happen, you can get an elimination reaction to kick out water and give you a protonated form of the product. Now all we need to do is use water to deprotonate this carbonyl, and we get to our final product, which is an enal, which comes from alkene and aldehyde. We also call these an alpha-beta unsaturated aldehyde. So you'll have noticed that until now we've been using two of the same molecule to react with each other. That's because it's really difficult to get control of which enol you would form and which would be the electrophile if you have two different carbonyl sources. So one way you can accomplish that, that's called a crossed aldol, is to have only one of your carbonyl compounds actually have enolizable carbons. So here this carbonyl has an alpha carbon that has two available hydrogens to deprotonate, also on this side. So it has 4 total hydrogens that are available for deprotonation. But if we look at this aldehyde, on its alpha position is a carbon that's involved in a fully substituted bonding pattern. Specifically, it's in this benzene ring here. And so there is no CH bond here to deprotonate, so this cannot undergo enolization. It'll just get activated and kind of hang out there. Meanwhile, this one can become an enol, and that will attack here to give the intermediate beta hydroxyketone, and then that will undergo elimination to form the final product. So we'll go ahead and draw that. We're activating the carbonyl. Now we deprotonate to form the enol. And now here's an important point. We want to use a carbonyl that is going to be more electrophilic than this compound in order to favor the crossed aldol product. Of course, that aldehyde has to also be activated before it can undergo attack by this enol. So again, we're going to form the enol. We activate our leaving group and we kick it out. Finally, this will be deprotonated to give the neutral product. So at the bottom there are some non-enolizable aldehydes and a non-enolizable ketone, so you can use those for some practice mechanisms with the cyclopentanone starting material. Another modification of the crossed aldol reaction involves using one reagent that's much more acidic than the other, so that you primarily get the nucleophile on that species. So here we have nitromethane, and this reaction is under basic conditions, so we're going to directly take our hydroxide and deprotonate the acidic proton on nitromethane. And now we basically treat this as if it were our enolate. We can reform the carbonyl, add to the other carbonyl, and give electrons to oxygen to get to a tetrahedral intermediate. Then we simply protonate this oxygen to get to the product here, and that can be handy in the synthesis of alpha amino alcohols because you can subsequently hydrogenate the nitro group using H2 and nickel to access a primary amine. So that makes the alpha amino alcohol, which gets its name because relative to the carbon that has the oxygen, it's on the alpha carbon. So if you want to do an aldol reaction that uses two enolizable carbonyl groups, then one option is to use a Reformatsky reaction. So you would do an alpha bromination of one of your carbonyl compounds. So here we did so with ethyl acetate, just treat with acetic acid and bromine to put on this alpha bromo group, and then we treat with zinc. That's going to insert into the carbon-bromine bond, just like in the Simmons-Smith cyclopropanation, to give an organometal species. And remember that we can kind of think about this intermediate as being like a negative charge on the carbon and a plus on the zinc. So if we think about it that way, it makes sense that this will actually rearrange to form the O-enolate, where you have the zinc on oxygen and the carbon-carbon double bond. Now this enolate is going to be ready to add to this carbonyl compound. So we reform the carbonyl, we attack with the pi bond, and we form an alkoxide there. Our final step is to protonate this intermediate, which we will do during the workup. So life just keeps getting better. Now we can do this in a circle, an intramolecular aldol reaction, or following beta elimination of the hydroxyl group, you would get the intramolecular aldol condensation reaction. So you're going to want to start by numbering your atoms so you can see which carbons are going to attach where. So the carbons that have an oxygen attached to them are carbons 2 and 6. So we can place those here. When we do that, it becomes clear that this must be carbon 1. This is 3, 4, and 5. So what this is telling us is that we're going to need to enolize over here and then we're going to form a carbon-carbon bond between that position and position 6. So since we've been doing a bunch of acid-mediated ones, we'll do a base-mediated approach on this slide. So we'll go ahead and deprotonate here. We form our carbon-carbon double bond, and we push our pair of electrons up onto oxygen. That gives us this intermediate, which we can redraw in the orientation of the product to make it a little bit more clear what's going to need to happen. So you can see that when you rotate the molecule around, carbon 1 and carbon 6 are actually in pretty close proximity. So we reform the carbonyl. We use these pi electrons to attack, and then we push up that pair of electrons onto the carbonyl. That leads to the deprotonated version of the first possible product, and we hadn't specified yet whether we're being heated or not. So if there's heat, we'll go this way. If there's not heat, then we simply protonate that oxygen and we get to our final product. In the case where we do have heat, we're going to go ahead and do a reaction similar to what we saw in the previous slides. We're going to first form this enolate and then do a beta elimination of the hydroxide. And the reason we need heat for this is that kicking out this hydroxide here is a relatively high energy step. But then it makes a very stabilized product, which is this alpha beta unsaturated ketone, which is also called an enone. Also, this process here where we deprotonate next to the leaving group and then that anion ends up kicking out the leaving group is called an E1CB reaction, E1 conjugate base. So it's analogous to an E1 reaction because the elimination step happens in a unimolecular fashion. That's what the 1 stands for. But it requires the formation of the conjugate base of the starting material for that to happen. So we form the conjugate base of this ketone, which is the enolate, and then that enolate aids in the departure of the leaving group in the elimination step, but no base is involved in the step where the leaving group leaves. So it's E1CB, conjugate base. So next we'll take a look at Claisen condensation, which is a really similar process to the aldol reaction, with the exception that because we're now going to be starting with 2 equivalents of an ester, we have a leaving group to depart when we add the enolate of our first starting material with the second molecule of starting material. And so that's going to result in the formation of this beta keto ester instead of forming either the beta hydroxyketone or the enone product. So if we are referring to the ester in the name, then alpha to the ester is this carbon, beta to the ester is this ketone. Also, because we have this ester moiety, we typically use a base that, if it's going to be nucleophilic, will match with the ester functionality that we have here. So we don't use sodium methoxide to do a Claisen condensation with an ethyl ester because you would end up with O-methyl over here as well. So you would do the Claisen condensation part, but you would also do a transesterification. So that's why we like to match what kind of group is on the ester with what our base is. Similarly, we match the solvent to that base and to that group. So we have a base, so you want to ask yourself, what's the most acidic position? Of course, it's pretty straightforward here because there's actually only one carbon that has any protons on it. So that must be the most acidic position. We can go ahead and deprotonate to form the enolate. And then we're going to go ahead and add to this carbonyl, and we need to form a tetrahedral intermediate. We know we need to kick out a leaving group to be able to form that beta ketone, and so we can go ahead and do that here, kicking out ethoxide. So that gives us our final product, the beta keto ester, and again this reaction is the Claisen condensation. When we do the Claisen condensation intramolecularly, it's known as a Dieckmann cyclization. So again, it's going to help you out if you go ahead and number your carbons. So we'll ignore the ethyl groups because those are on the ester and we can see where that ends up here. Okay, I've numbered 1 through 6. And of course, if we're going to make a ring and we're going to be using an enolate as our nucleophile, then we have to start from one of the carbons next to a carbonyl. So we can make a bond between carbon 2 and 6 or between carbon 1 and 5. They're chemically equivalent, so it doesn't matter which one you draw. I'm going to deprotonate at position 5 because it's closer to where I drew the ethoxide. Again, it's helpful if you draw the product, or the intermediate rather, in the conformation of your product so that you can see where all the atoms go. Okay, so we're going to push down our lone pair to reform the carbonyl. Our nucleophilic carbon is at carbon 5. That's going to attack at carbon 1 to make a new tetrahedral intermediate there. So next we're going to use this lone pair to help kick out our leaving group. And I'm drawing this down here because even though this is the desired product, it's not stable in the reaction conditions. This hydrogen here is too acidic and it's going to be deprotonated by the ethoxide to form this enolate. And this is where the molecule is going to hang out until the reaction is complete, and then we'll do our workup where we add aqueous HCl. I'm just going to write H3O plus here because you have the reagents above. And so now we can put this carbonyl back down, and we're going to protonate on the pi bond. And that's going to give us our final product, the beta keto ester. The last thing we'll talk about today is the crossed Claisen. So this is similar conceptually to the crossed aldol in that you're going to have one precursor ester that has a carbon that has enolizable position, which means it has a CH bond on it. It actually has two, but we're just going to draw the one that we need. And then the other product should not have any alpha CH bonds. So remember, this is the alpha position. This is an alpha CH bond. So we have a base, sodium ethoxide. And so what we need to react with our base is going to be an acidic proton. And so here is the most acidic proton in this molecule. We deprotonate, make the enolate. So now we're going to react the nucleophilic carbon with the electrophile with the help of that oxygen lone pair. We push the electrons up to get to this intermediate. And then again, we just need to kick out our leaving group. To get to what will eventually be our product, but since we're in a solution that has sodium ethoxide and ethanol, and the pK of ethanol is about 19, pK of this H atom here is about 11. So what that's telling us is there's going to be a strong preference for the proton to be attached to the ethoxide in the form of ethanol rather than staying where it is on the molecule. It's almost a pKa gap of 10, which means this is a nearly irreversible step. So this is going to actually get deprotonated, and you're going to form the enolate where the negative charge will be on the ketone oxygen. And now when we do our aqueous HCl workup, we're going to protonate our enolate to get to the final product.